Hi, I'll be now presenting part 1 of homework number 2, in which we were tasked to implement the model of the dynamic equations of a synchronous machine. Important to note that in this model in particular, we are assuming that the rotor is isotropic. That means that LD and LQ hold the same value, hence why in this model in particular, as we can see, LEQ appears instead of LD or LQ. Also, we are assuming that the motor has magnetic linearity. That means that the inductance is independent and does not change from the position of the motor. So going into Plecs, as we can see, this is our implementation of the set model. As we can see, we have reference ID and reference IQ being fed into the subtractor. That it is being subtracted by the real ID and IQ. So this error, they're individually being fed into PI controllers, and that output of the PI controllers are fed into this, which are basically um, the model of the dynamic equations. These two blocks represent the electrical poles of the motor, and these two are for the decoupling. The decoupling of each current, and this one is the decoupling for the back EMF. So to see if it is following correctly the reference, let's say that let's put first a simple reference of 5. As we can see, it is correct. Our model is following correctly the reference in the steady state. This is IQ, this is ID. ID is set in 0, as we can see here. And in fact, as we can also see, the speed is also steady and constant in the steady state. So changing it for multiple steps, let's say 3 and -4. We're going to simulate it. And as we can see, it also IQ. It does follow correctly, although it does present a bit of undershoot and, well, overshoot in this case, as we can see. ID also presents a bit of overshoot in the current, and as we can see, the speed does follow correctly. So now in regards of the graph of speed versus applied voltage, we are going to calculate applied voltage over here, being the magnitude between VD and VQ, that are the outputs of each PI controller. And the graph is this one, respectively. As you can see, our motor does present almost a completely linear behavior between the speed and the total voltage applied. So now regarding the torque controller, it was pretty simple to implement, since the relationship between the torque applied by the motor is kind of linear in regards to IQ, since our synchronous machine has the same value for LD and LQ. The equation that relates torque with IQ is written by this one. So to make the torque controller, we just need to apply the inverse over here. So to test if this does work, we're gonna put the step of, let's say, 10, 0, and 0, and we are going to see that it is in fact following the reference. Now testing for multiple steps, let's say 10, let's say -5, and then another 10, we are gonna see that it also does successfully follow the reference, although it does present a bit more undershoot. So now, lastly, and with the speed controller. And to implement the speed controller, what we did was implement another PI controller for the speed, shown over here. It is in Cascade. So here we have the reference speed being subtracted by the real speed, and that error is fed into the PI. So putting reference, we're gonna say a reference of 10, 0, and 0. We are going to successfully see that, oh, sorry. We are going to see that the speed does in fact follow pretty accurately the reference. So now testing for multiple steps, let's say 8 and -3, we see that it does in fact follow the reference. So important to note that our constants of the inductance of the resistor, of the pair of poles of J, and the linkage flux are all obtained from this model of the Kolmorgen AKM740, which is one of the motors we found that was appropriate for the application of the viscous fluid. So hence why we used it, and their constants are all over here. These are the constants for our PI controllers. These two in particular are the constants of PIs for the both currents, and this one in particular is are the currents for the constants for the PI controller of the speed. Thanks for listening.
Well, this is our permanent magnet synchronous machine DQ current control system. We took the motor in the Plecs motor and we set all parameters in one to make easier the calculus and the analysis. We connect to the motor a torque load controlled by the angular speed of the motor. With this probe, we measure the stator first current, the rotational speed, the rotor position. This signal is in fact the angular speed. We operate with a square function with Plex modules, and we multiply them with a -1 0.05 constant. The -1 is for the direction of the torque to make load to the motor. Okay, this is our mechanical system. To operate our mechanical system, we have the inverter. This module will be explained later by my partner, but it's a PWM generator. We have two park converters, one for the actuation. The voltage in the DQ voltage are transformed to a ADC voltage that get in this inverter module, and other one of the park modules convert the ADC currents to DQ currents to implement the PI control system. Yeah, for the PI control system, we have three feed forwards to cancel the coupling between the machines. This first feed forward is for the quadrature current. This is just lambda plus angular speed. This is not for the coupling, but it still improve the performance of the system because the controller don't have to care about this component of the voltage in the quadrature X. Yeah, the next one is again for the quadrature current. For the quadrature actuation. This is the actuation node. It's the inductance plus the direct current plus the angular speed. And this other one is for the direct current, that it's -1 plus inductance plus current, quadrature current plus angular speed. These modules what do is to transform the system that the PI controller see. If we don't have these parameters, the system is too complex for a single PI controller. Yeah, we have another one, feed-forward signals, that they are the DC voltage signals. Like if the resistance of the quadrature axis is 1 ohm, and we want to have 10 amps, we know that in zero frequency we will need a voltage of 10 volts. This is what these modules do. This is just a one multiplying the reference signal. This is because the resistance of the machine is just 1. The same for the direct current. I want the resistance multiplying the reference current that adds directly to the actuation node, and this is the controller. That's all. To test our system, we put a constant reference and a steps that are in this step in the quadrature current. It's about the 3.3 seconds of the simulation, and this other one is for the 6.6 seconds of the simulation. The simulation took 10 seconds. We're simulating about 1 microsecond because the system is more stable. The simulation is more stable. It takes a lot of time, but this is the signal. At the beginning, the reference current for the quadrature axis is 2 amps, and we can see that about 0.3 seconds, the quadrature current is just converged to the reference, and at 3.3 seconds, the step in the reference are perfectly controlled by the system, and we can see this segment that we can see here that the interference between the two axes is just like 0.0006 amps. It's just too low, and in this section we can see that the coupling is too low. Again, it's where's the scale? Yeah, the scale is 1 to 1. Then the variation is like 0.001 amps. This is a proof that our two axes are independent with the feed-forward signals. Well, we can see the angular speed and the currents. We can see that if we put a constant reference to the direct and quadrature currents, the ABC currents are sinusoidal. That's logic because the motor starts to spin. It has torque and an inertia and a load, and the speed becomes to go up, and the frequency of these currents start to grow. Yeah, the position, the angular position, it's just between P minus P and P. It's the complete circle and resets, and the frequency becomes higher than the time pass.
This is the subsystem. It receives 3 signals that come from the PID controller in the ABC coordinates, not the DQ coordinates. Each is a reference for the respective phase of the voltage for the sinusoidal wave of a determined frequency. It goes to the non-inverting input of a comparator, and the triangular wave goes to the inverting input of the comparator. At the output, we could receive either a 1 or a 0, but the 0 is turned to a -1 just to be coherent with the working principle of the converter. This is done with the C script block here. This information is gathered here in the multiplexer. We can see the information for each phase and the control signals, these orders for the inverter, and are rectangular waves as we could expect, oscillating from 1 to -1, and so on. This inverter is supplied with DC voltage, and at the output we will receive the control signals that are sent to our synchronous motor of permanent magnets. I placed here a voltmeter just to see what we are getting from the inverter. As we can see here are rectangular pulses, and they all grow the distance between them. This is because we are coming from here on the left from the maximum of our sinusoidal wave that is modulated through pulse width modulation, and the average value now is decreasing. At the output is the PMSM, as I said before, and the PMSM, since it has inductors, it will filter, like a low-pass filter, the signals that are coming for each phase. So it will integrate this rectangular wave, and it will grow a little, grow a little, grow a little, with some harmonics, but not so much in this case, in this simulation. This is the control signals and actuating signals that go to the motor itself.